What is energy? You get energy from the foods you eat. When you're running out of energy, you sleep to regain it. But it's so much more than that. Energy is the driving force that powers the universe. It's what makes the world go round. It's what gives people the light to read by. Without energy, you wouldn't be here. The kind of energy we can manipulate to our advantage is the energy we derive from the world around us.
Efficiently utilizing Earth's power and energy has long been a test to humanity. Back before oil and coal were in use, we relied on fire. We created fires to cook and to keep us warm. Then we discovered coal and steam-powered things. It was an abundant and cheap resource. We now had something that could burn twice as long and twice as hot as firewood. We then discovered oil, which even furthered our addiction to flames. However, over time, we discovered that these fuels were not great for the environment, and we were exceedingly dangerous when improperly used. Effects of burning these fuels included pollution and effects such as acid rain, and in turn, hydropower was developed, using water existing to heat power out of our homes.
We used the energy from the wind and then from our biggest power source, the sun.
But it wasn't enough. These sources were great for alternative energy, but couldn't provide the power to fuel millions of homes at a time. No source could replace either coal or oil. There are many forms of energy and power, but how do we know which is the best for us in our environment? Let's take a look at a car. Most engines run on some form of diesel fuel. Diesel is a powerful resource, but it has negative effects on the environment. We do have a replacement being developed, however, known as biodiesel. Biodiesel is an easy-to-make but hard-to-use type of fuel. Essentially, biodiesel uses unusable resources from plants and animals as a replacement for the original diesel fuel that we use every day. Sometimes dangerous. Biodiesel was first invented by two scientists named E. Duffy and J. Patrick in 1853, but it was largely unused until Rudolf Diesel's invention of the diesel engine in the 1890s. Diesel engines can burn a variety of different fuels, making them the almost perfect engine to burn natural fuel. Dr. Diesel wanted to have his engine run more efficiently, and in his later years, he worked with the French to create an early form of biodiesel. The French vision for biodiesel was ahead of its time, as the technologies of the late 1800s and early 1900s could not produce a sufficient supply of alternative fuel. In the 1900s, Rudolf Diesel worked with French scientists to create a form of organic gas for their African colonies to produce.
My engine will allow a better and hopefully cleaner way to power our trains. It runs on certain types of pure vegetable oil. It works on the principle of compression, ignition, in which fuel is injected into the engine cylinders after air has been compressed to a high pressures temperature as the fuel enters the cylinders. It's something nice forcing the piston back and down, converting the energy into mechanical. I call it the diesel engine!
E. Duffy and J. Patrick first started attempting to create different forms of biodiesel from fat, vegetables, and other varieties of renewable fuel in 1853. The clean, renewable, and environmentally healthy fuel that they created could be our source of fuel in the future. And even now, scientists test and retest any and all forms of biofuel to find the best form of renewable energy. However, Rudolph's attempt at a clean universal fuel that could power our world fell on deaf ears. Oil companies and car manufacturers sought cheaper ways to fuel the growing automobile age.
Let's take a look at what biodiesel is. Biomass is any energy taken from living organic material, including wood products, aquatic plants, field products, etc. We take energy from organic materials when we eat. So shouldn't our engines be able to do the same? There are plants and animals all around us that we can borrow energy from, creating a renewable source of energy.
Rudolph's diesel engine was a great invention, but it wasn't quite what we know today as biodiesel. Biodiesel is an alternative to standard diesel fuel, made from vegetable oil or animal fat. We're taking the parts of our food that we don't use and using them to create energy to power our cars. It can be used in engines that run on diesel fuel. But what difference does it actually make? Sure, we're conserving our resources, and that's amazing. But that's not the only benefit of biodiesel.
Diesel fuel releases many toxins and pollutants, such as carbon dioxide and carbon monoxide, into the air. With biodiesel, these emissions are cut in half. Biodiesel is also a much better lubricant than petrodiesel, extending the working life of your engine. When burnt, it gives off fewer particulates, which reduces respiratory problems. It is also much easier to ignite, making it a much more efficient combustion.
There are downsides to this seemingly perfect source. If we use biodiesel on a wider scale, it will likely become another big monopoly like oil. If this happens, plants will be grown more often for oil instead of food, making it harder to feed the population of less economically developed countries. Ethanol and biodiesel are much more expensive than the fuels they replace, and a lot of it is required as it gives off less energy.
Even if you choose not to believe in global warming, and even if you choose not to believe that mankind is affecting the earth through the greenhouse effect, burning gasoline and other fossil fuels does more than just warm the earth up. It puts toxins and poison into our air. The greenhouse gas effect is basically what keeps us alive. When CO2 is in the atmosphere, it traps some of the heat from the sun and keeps the earth warm during the night or when the sun is not pointing directly at us. If it wasn't for that, we wouldn't be around. However, thanks to fossil fuel burning and lots of other factors, there's too much CO2 in the atmosphere and more heat than we need is being trapped.
The Industrial Revolution was a tremendous milestone in our history. It boosted our economy extravagantly and spawned an entirely new era of continually growing technology. However, for every action there is an equal and opposite reaction. The downside and the price of this illustrious expansion of technology? Acid rain. It causes damage to our plants, animals, and ourselves. Although we don't feel the effects of acid rain on our bodies, it still affects us. The damage acid rain has on our plants puts our food sources in jeopardy and threatens even the monuments we built to stand the test of time.
Despite these terrible side effects that arose from overpopulation, it was not until recently that government regulations were put up to hinder the destructive rains. But what does pollution have to do with rain anyway? Is this just another vain attempt of government to control us? If only the problem was that simple.
The pollution that is released escapes up into our atmosphere as gas, where it gets caught in dense rain clouds. These clouds contain water that precipitates in the form of rain, and rain contains the same pollution. This polluted rain, or acid rain, falls onto our plants, animals, and our bodies. Acid rain, a type of pollution. It is rainfall that is more acidic than the regular neutral rain. It is caused by sulfur dioxide, or SO2, and nitrogen dioxide, or NO2, from industries burning fossil fuels. Over the course of the next several hours to several days, the pollution that is caused by SO2 and NO2 becomes acid rain. When that acid rain falls, our natural environment is slowly destroyed and broken down, hurting many water-based animals such as fish and destroying some man-made items such as statues. In 1971, in a lush Connecticut forest, a scientist and Yale University professor by the name of Dr. F. Herbert Borman and his team first discovered the threat of acid rain.
Golly gee, this rain is incredibly acidic.
In order to discover the reasons behind this acidity, Dr. Borman, Dr. Jean, and their team studied the acid rain in the eastern United States for the next year. Collecting their research, they attempted to present it to the world.
Okay class, today we are going to be learning about acid rain. Acid rain pH levels have gone up 1000% since the 1950s.
The scientists traced the acidity in the rain to sulfur dioxide emissions and various nitrogen oxides from faraway smokestacks. The gases are converted to sulfuric acid and nitric acid in the air and then are precipitated in the form of rain. In 1974, Borman published the effects of that acid rain had on wildlife and nature.
We need to take more care in preventing pollution to protect our forests and wildlife.
I agree!
I agree too!
The main cause of acid rain is the industrial burning of coal and other fossil fuels. When the waste gases form, they contain sulfur and nitrogen oxides, which combine with the atmospheric water to form acids, creating acid rain. Dr. Borman was instrumental in the passing of the Clean Air Act. He passed away just 2 years ago. Today, scientists from all over the world are working together to prevent future damages from acid rain. The discoveries made by these scientists will help not only prevent the dangerous effects of acid rain, but will also help save our energy future.
Nuclear energy, a resource that has the power to wipe out entire cities, but when controlled, gives us a vast amount of renewable energy. You may have heard conflicting arguments about the potential of this incredible powerhouse. The terror of the power used in the Cold War is not an easy idea to sell to the people. Even so, it has more potential than any of the other sources of power to create more energy than we could ever thought imaginable. I am here to tell you exactly what we mean when we mention nuclear energy. Let's see how it works. Let's start with the basics. All elements have their own atomic number and their own atomic weight. The atomic number is equal to the number of protons, which are positively charged particles in the atom. It's also equal to the number of electrons, which are negatively charged particles. This is what identifies one element from another. The atomic weight is the average weight in AMU of a single atom and its variations of the said element. The atomic weight is the number of neutrons, the particles with no charge, the protons, the positively charged particles, added together. However, not every atom of the same element will have the same amount of particles. Sometimes you will have what are called isotopes. An isotope is an atom with an unbalanced amount of particles. These isotopes become unstable pretty easily, or radioactive as scientists call it, when its number of neutrons is too great to maintain. An atom also becomes unstable if its atomic number is greater than 82. Radioactivity is the process of the isotope becoming stable again. To do this, the isotope undergoes transmutation, which changes its atomic number, and it actually becomes a different element. It also releases energy. This energy is called radioactivity that we have learned to know and fear. Radioactivity takes 3 forms, named after 3 different letters of the Greek alphabet, and in the order that they were discovered. Alpha radiation contains positively charged particles that are identical to the nucleus of a helium atom and have 2 protons and 2 neutrons. These are the biggest forms of radiation particles and the most potentially harmful to humans. However, they can be stopped by most substances, including paper and even your own skin. The next form of radiation is beta radiation. Beta particles are high-energy, high-speed electrons, or positrons, which are positively charged electrons. If a nucleus has too many neutrons, it will undergo a beta decay, in which process a neutron is converted into a proton and an electron. The third form is gamma radiation. Gamma radiation is exerted not as particles, but as rays, which means it is made of photons or light itself. This happens because it has such a high energy that it cannot have a physical form. Gamma decay happens when energy states of a nucleus is too high. During radiation, the nucleus also releases energy in the form of heat. This energy can be used to our advantage. There are 2 methods for nuclear reaction to happen: fusion and fission.
Nuclear fusion is when 2 separate nuclei collide at very high speeds, fusing together to form a new type of atomic nucleus. During this process, some of the particles are converted to photons, like in gamma radiation. This happens naturally in our sun, where hydrogen atoms are fused together to create helium. Nuclear fission is when a single nucleus splits into 2 smaller nuclei. This process produces a small number of neutrons and protons, which cause a chain reaction, meaning that it causes its surrounding nuclei to split as well.
We use the energy produced by nuclear fission for many purposes. It is the main component of our atomic bombs. You may have known about the atomic bombs of Hiroshima and Nagasaki. The destruction that came from those bombs was unmatched by any other form of weapon at the time. The energy produced by fission is so great that it can wipe out entire cities. When contained, however, nuclear reactions can be used to give us enormous amounts of power. We can harness that energy through our nuclear reactors.
This is what a nuclear reactor looks like on the inside. Looks pretty complicated, doesn't it? It's actually quite simple. It uses the fission produced by uranium-238, an extremely unstable isotope, to generate heat. In the reactor core where the fission takes place, there's a big block of things called fuel rods, carbon moderators, and control rods. These rods help to keep the reaction from going out of control by absorbing excess neutrons. The heat generated from the chain fission reaction is used to create steam. To keep the machine from overheating, they have a series of coolants running through. The steam is moved through an electrical output where it generates electricity. After it is all used up, the steam goes through a condenser, which turns the steam back into water to be used again. You may have mixed feelings about this. You have probably heard about how dangerous radioactivity can be, and may feel uncomfortable about having the same process used in an atomic bomb generating your electricity. You may be thinking, am I in danger of being exposed to harmful radiation? The answer is no. The background radiation you are exposed to by living near a nuclear reactor is nothing compared to what you are exposed to by smoking, getting an X-ray at an airport, or even from your food, water, and air. Nuclear reactors make up less than 1% of your daily dose of radiation. Remember, there are people who work at nuclear reactors every day. Of course, if you stood directly in the reactor core, you'd be killed almost instantly. But the core is surrounded by a thick concrete wall that can only allow a negligible amount of radiation to pass through, meaning the harmful stuff is kept far away from people. Now, you may have heard stories of nuclear meltdowns, such as the plants in Fukushima after the earthquake. It's understandable to feel nervous about it, but the danger is largely blown out of proportion by showing the worst case scenario. People's main concerns come from the stories of Chernobyl. The 1986 disaster of Chernobyl, a nuclear power plant in Ukraine, was the product of a flawed Soviet reactor design coupled with serious mistakes made by the plant's operators. It was a direct consequence of Cold War isolation and the resulting lack of any safety culture. The accident destroyed the Chernobyl 4 reactor, killing 30 operators and firemen within 3 months, and several further deaths later. One person was killed immediately, and a second died in hospital and was soon after as a result of injuries received. Another person is reported to have died at the time from coronary thrombosis, an acute radiation syndrome. After the disaster, local Ukrainian authorities, with the aid of the Russian federal government, came in to help clean up the mess. When a nuclear reactor fails, it leaves quite a big one. 237 people on site and involved with the cleanup were later confirmed as casualties. 134 of them died. Of these, 28 people died of direct exposure to the radiation. Nobody off-site suffered from acute radiation effects, although a large portion of childhood thyroid cancers diagnosed since the accidents is likely to be due to an intake of radioactive iodine fallout. Furthermore, large areas of Belarus, Ukraine, Russia, and beyond were contaminated in varying degrees. Ironically, the disaster occurred during an experiment to test a new... start over. Ironically, the disaster occurred during an experiment to test a newly added emergency core cooling feature. When this new cooling feature failed, it failed badly. But it wasn't the fault of the workers involved, or of some sort of snowball effect. The Russian government at the time was urging them to test the reactor to its limit and past the point of safety. This was a very unfortunate incident, but with modern technology, could have been avoided very easily.
Unfortunately, events like Chernobyl can happen, but they're not very likely. Nuclear reactors are built to not only avoid catastrophic meltdowns, but to warn you before they happen. Thanks to government regulation and improvement in technology, each part of the reactor is equipped with a backup system. If something fails, they have a backup system, and a backup system on the backup system, and so on and so forth. It is possible for all of these backups to fail, but the probability is so exceedingly low that it will never happen in your lifetime. There are enough people working to prevent meltdowns that only under very special circumstances could one actually happen. Despite improvements in safety, one mistake of nuclear planning is to put the plant in a densely populated area. However, in America, most power plants are placed in places where there are few people as possible, like in the middle of the Arizona desert. A meltdown is the informal term for a severe accident in a nuclear reactor that causes the core to overheat and become damaged. Statistically, this might be expected to happen once per 20,000 years of operation in a single plant. In 2 out of 3 of these meltdowns, there would be no casualties. In 1 out of every 5, there might be more than 1,000 casualties. In 1 out of every 100,000, there might be more than 50,000 casualties. On average, there would be about 400 casualties for all meltdowns. The air pollution caused by coal burning caused an estimated 10,000 deaths per year. This means that in order for nuclear power to be as dangerous as burning coal, there would have to be 25 meltdowns every single year.
Another source of concern is nuclear waste. After a nuclear reaction takes place, the water used in the cooling process stays radioactive for a long, long time. There isn't much you can do with it at that point. Scientists have found a way to convert the waste into a solid form so that it takes up less space and is more easily contained. But at the moment, this is not cost effective, so we still wait for an ideal solution. Spent fuel rods are another source of nuclear waste. Once the fuel rods have become spent, They can't be used anymore and have to be replaced every 18 to 24 months. They place the fuel rods in a big pool of water to let them cool down. After they are cool enough to be handled, they are buried along with the other waste. Many people hear the word radioactivity and automatically associate it with danger. The media can sometimes blow the danger out of proportion, but that's not the case. Radiation is actually used to treat and diagnose diseases. You've probably gone to the dentist before and had them x-ray your mouth. That's radiation. Without radiation, we would have very limited resources for medicine and research, and more deaths would be caused by that than by radiation itself.
Nuclear power is such a potent resource that if we were to power a car with nuclear fission, this car would be able to run for 20 years without refueling. Now that's efficient.
In 1938, two German chemists named Otto Hahn and Fritz Strassmann, and two Australian chemists named Lise Meitner and Otto Robert Frisch, conducted experiments with neutron-bombarded uranium and determined that the teeny neutron split the nucleus of the large uranium atoms into two equal pieces.
The nucleus, it's split in half.
Split in half? But how?
This process they dubbed fission, as a reference to biology, completely ruptured the nucleus. This was very surprising. Later, a scientist named Leo Szilard found that if these fission reactions released extra neutrons, it could create a self-sustaining nuclear reaction.
Go.
The energy created from this reaction is strong enough to win the war.
Really?
No. Yes.
Many countries petitioned their governments to allow further fission research in order to develop nuclear weapons, as World War II was just around the corner. In the United States, Chicago Pile 1 was the world's first man-made reactor. It was created on December 2nd, 1942. This became part of the Manhattan Project, a secret U.S. program organized to explore the creation of an atomic bomb. The reactor's purpose, such as the Chicago Pile 1, was to create plutonium, uranium-238, to decay. This plutonium was to be used in the world's first nuclear weapons used on Hiroshima and Nagasaki. In 1953, President Dwight Eisenhower made a speech at the United Nations called Atoms for Peace. This was followed shortly by the 1954 amendments to the Atomic Energy Act, which declassified the reactor technology and encouraged further development, spawning a new era of energy. Today, scientists are working using fusion instead of fission in their nuclear reactors. Fusion is much more efficient and produces less waste, but requires an extremely high temperature. In fact, the only place that we know this reaction takes place naturally is in our sun. But that doesn't mean we'll never be able to create fusion here on Earth. Nuclear technology is still a young idea, and scientists are still working to perfect it every day. The future of nuclear energy is a bright one, but we still are left to wonder, is there a better source of energy out there, better than all of our current resources? Probably. There's no telling what the future has in store for us, and we'll always be searching for new ways to improve. But until we find that perfect source of an indefinite energy, we'll make the best with what we have. We've come a long, long way from relying on fire alone, and we can only go so much further.